Hello, my name is Shuji Nakanishi. I'm serving as a professor of Research Center for Solar Energy Chemistry. That is a joint center of Graduate School of Engineering Science Osaka University. Our laboratory is interested in researches of green chemistry for saving our planet. Throughout this movie, I'd like to share the research activities of my laboratory. Have you ever heard of the Anthropocene? The Anthropocene is a classification that includes the present day in geologic time, proposed to focus on the impact of humans on the Earth's geology and the ecosystems. The Anthropocene is characterized by climate changes, including global warming, loss of biodiversity, and increasing in man-made materials, and also changes in sediments due to fossil fuel burning, all of which are attributed to human activities. Especially after the World War II, socioeconomic and the global environmental changes increased dramatically, and this period is called as the Great Acceleration. Thus, human activities have had such a significant impact on the global environment, so that discussions for defining a new era classification have arisen. Actually, a global anthropogenic CO2 emission reached 25 to 30 gigaton per year, which is equivalent to approximately 80 times the flux of CO2 due to volcanic or tectonic activities in nature. Human activities are therefore causing major disruptions to the global carbon cycles, and this situation must be addressed. Thus, on today's Earth, there is an imbalance between CO2 emissions from human activities and CO2 fixation by photosynthesis. There are two possible approaches to optimizing the carbon cycles and achieving carbon neutrality. One is to reduce CO2 emission in existing technologies and lower the weight of the left side of this balance. This is definitely an important task that human beings must urgently address. However, this effort alone will not achieve carbon neutrality. Looking ahead to the future growth of the world population and also the global economy, it is essential to develop another technology to fix CO2, namely an artificial photosynthesis technology. From this standpoint, we are challenging these important missions based on chemical approaches. In order to mimic photosynthesis, at the first place, it is necessary to understand the mechanism of natural photosynthesis. As you know, in photosynthesis, organic compounds are obtained from water and CO2 using sunlight as energy source. Photosynthesis takes place in chloroplast, which is around 1 micrometer in size. Light absorption by chlorophyll molecule is the first step of the light to chemical energy conversion process. In this mechanism, photogenerated holes oxidize water and resulting in the injection of electrons into the photosynthetic electron transport chain. Then the photoexcited electron are eventually used for the reduction of NADP plus to produce NADPH. In conjunction with the photosynthetic electron transportation, a proton motive force is generated in the thylakoid, upon which ATP is synthesized from ADP with a proton motive force of driving force. The NADPH and ATP thus produced in the right reaction are subsequently used for the fixation of CO2 to form organic substances during the Calvin cycle. The individual reaction that supports entire the photosynthetic energy conversion are controlled by highly functionalized enzyme. Mimicking or artificializing such enzymes that life has established over its long evolutionary history will be impossible with current human scientific capabilities. However, on the other hand, it is possible to mimic the functional aspect of natural photosynthesis. With this in mind, let us review natural photosynthesis in terms of chemical reaction. In photosynthesis, electrons are extracted from water oxidation reaction, are energetically excited by sunlight. Then, the excited electrons are used to reduce CO2, forming organic compounds. In this light, artificial photosynthesis can be redefined as a system that connects the water oxidation reaction and the CO2 reduction reaction using sunlight energy. Although there are various types of artificial photosynthesis systems, we are working on systems in which CO2 electrolysis is integrated with solar cells. Solar cell technology is highly mature and energy conversion efficiencies approaching 50% are possible under the optimal condition. In case CO2 electrolysis is incorporated in an integrated system, it is necessary to fabricate a composite device that includes catalysts, electrodes, ion exchange membranes, and other components. And such a system are more complex than those associated with a method using photocatalyst powder. However, importantly, the energy conversion efficiency in this method could be, in principle, much higher than the others. Besides, the integrated process are able to provide high reaction rates even at ambient temperature, pressure, and also 2 carbon to 3 carbon, 4 carbon compounds would be obtained if appropriate selective catalysts were developed. Furthermore, the working potential of the catalyst, that is a very important determining factor of the reaction selectivity and activity, can also be precisely and dynamically tuned by adjusting the external applied electrode potential during the electrolysis. Consequently, various reaction products can be generated as required. The concept of integrated artificial photosynthesis allows us to optimize each component technology individually, but each component needs to be connected to establish a unified system. An appropriate design for an entire system is thus mandatory, including the optimization of the capacity of the component elements. Among things to do toward the social implementation of the integrated artificial photosynthesis, developing effective catalysts is the most important for obtaining the target product with low overall potential, high current density, and high selectivity. The elementary reaction pathways of CO2 reduction on catalyst surface is complicated and to be elucidated further. But the current understandings depicted in this figure helps us discuss the impact of the catalyst surface on the selectivity on CO2 reduction. Thus, depending on the kinds of catalytic materials, we can obtain various CO2 reduction product. Although no catalyst material yet satisfies all the requirements toward the social implementation, we are now challenging to develop new chemical catalysts for the realization of the integrated artificial photosynthesis. To conduct such researches, characterization of newly synthesized materials is critically important, and our laboratory is equipped with advanced analytical techniques to analyze these novel catalytic materials at the atomic and molecular levels. In the CO2 reduction reaction, as I said, a wide variety of products such as carbon monoxide, methane, ethylene, ethanol are obtained. Understanding the correlation between catalyst materials and CO2 reduction products is also important for designing the entire system of artificial photosynthesis. Therefore, our laboratory is also equipped with advanced analytical instruments to quantify the wide variety of products. As I have explained so far, my research group is working on integrated artificial photosynthesis based on CO2 electrolysis chemistry. Although I could not touch on this video due to the time limitation, we are also conducting bioelectrochemical researches for obtaining deeper understandings of the energy conversion in natural photosynthesis, and also developing next generation rechargeable batteries for the effective use of renewable energy-derived electricity. The group has now about 40 members, two-thirds of whom are undergraduate or graduate students, and the remaining third are researchers from industry. These diverse members discuss and enjoy the researches with the philosophy of saving our planet. Don't hesitate to contact me if you are interested in working or joining with us, and let's think together for the future of our planet. Thank you.